All right, so this is section 1.5. So 1.5, we're going to talk about what's called a homogeneous or homogeneous linear system, right? So that term homogeneous or homogeneous, however you want to say it, basically it's a fancy way of saying you want to try to get to the zero vector, right? You may have heard that before in other applications, like they use it in like genetics and biology, right? Or even like if you have taken differential equations and differential equations, it's literally the same meaning. But for us, the homogeneous or homogeneous is a fancy way of saying you're trying to get to the zero vector, right? That's the point. So whether you think of it as a matrix equation, as a system of equations like this, or a vector equation, the point is we're trying to generate the zero vector. Okay. Now, just like we'll get to what this is saying in a minute, but just like we were doing before, no matter what you're trying to generate over here, the question is there no solution? Is there a unique solution? If there is a solution, is there infinitely many? Do you have a dependent, right? So it's either no solution, one solution, or infinitely many. Okay. Well, if you step back and think about it, if you're talking about a homogeneous system, right, this will always have an answer, right? I mean, think about that. Like, I mean, think about this system here. What if x1, x2, and x3 were all zero? Clearly, that would work. Zero, zero, zero would work. Zero, zero, zero would work, right? Even if you had different numbers, if all your variables were zero, then of course you're going to generate zero. So, if you're talking about a homogeneous system, you're trying to generate zero here, you will always have a solution. This is what's known as the trivial solution, namely x being zero itself, right? I mean, just about anything times zero is going to give you zero. In this case, even if it's a matrix times a vector, it's still going to generate zero. Okay. So if you're talking about a homogeneous system, then there will never ever be a situation where you have no solution. There'll always be one called the trivial. Now, the question is, are there more? Right? If there are more, then you would have a non-trivial solution. So basically, you're either going to have one solution, the trivial one, or you're going to have a dependent system and you've got infinitely many. Okay. Then you'd have a whole lot of other non trivial solutions. All right. So let's check this out just to see, make sure we're on board with this. Okay. We'll talk about this, what this is saying in a minute. In a minute. So think about how you would go about solving this. Whether this is all zeros, whether you're talking about homogeneous or whatever, you set up the corresponding augmented matrix, right? So it's 3, 1, -4, 2, -5, 6, 2, 8, -7. And then you would augment that with, in this case, 0, 0, 0, right? And then we row reduce. If you want to do that by hand, great. Just for time's sake, let's do it on here. So if I turn it on, so in this case, we do have a 3x4, right? So 3x4, this, these are this, there we go. Yeah, you just trust me, it'll change the lighting on here in a minute. So it's a 3x4. We got 3, 1, -4, 0, 2, -5, 6, 0, 2, 8, -7, 0. Okay. And then let me just check, make sure we put it in there right. Right, 3, 2, 2, 1, -5, 8, -4, 6, 7, 0, 0, 0. Okay. So if we do indeed row reduce this, right, you're going to get this. Okay. Now, well, here, let me just write it. So what you're going to get is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Okay. All right. So then what does this mean to me? Well, okay. So technically, yes, you could read off this as basically saying that x1 is indeed 0, then x2 is indeed 0, x3 is indeed 0, equals 0. Or you could write it as a vector, right? You could say the vector 0, 0, 0, right? So whether you think of it as three different variables or one vector, whatever. But the whole point here is you're going to get only the trivial. Okay. There's some more stuff here, but let me talk about the next one and then we'll come back and put this together. Different system, but the point is it's still homogeneous. So do the same basic idea. But augment the matrix 4, -1, 2, 0, 1, -3, 5, 0, 2, 5, -8, 0. Okay. Do the same thing. Well, let's change my A now. Still a 3x4, but now it's 4, -1, 2, 0, 1, -3, 5, 0, 2, 5, -8, 0. No, I don't want that. Let me just make sure. So we got 4, 1, 2, -1, -3, 5, 2, 5, -8, 0, 0, 0. Okay. And then row reduce that. That's crazy, but whatever. We turn it into a fraction. There we go. But here's the point. Now you have that complete row of zeros. So in this case, you're going to have more than just a trivial. You are indeed going to have a dependency. You've got a free variable. X1 and X2 are pivot. X3 is non-pivot. There's your free variable. So X1 and X2 are depending on X3. Or let me write that out. So we got 1, 0, 1 over 11, 0, 0, 1, negative 18 over 11, 0, 0, 0, 0, 0. Okay. All right, so there we go. But again, what this is saying is that, again, technically this is saying x1 plus no x2 plus 1/11 x3 is equal to 0. Or this is like your equal sign, you can move it over. So what that's really saying now is that x1 is really negative 1/11 x3, right? x2 minus 18/11 x3 is equal to 0. So if I move it over, then x2 would be 18/11 x3. And then row of zeros here, so then x3 is your free because that's the non-pivot. Again, you could write it like that, or you could write it as a vector if you like. Okay. Now, how would I write this as a vector? Well, x3 is your free variable. So you can kind of think of it as just kind of like, I'm writing x1, x2, x3, right? But if they all have an x3 involved, I can kind of like factor it out, or I can think of it as it's going to be a scalar multiple of some vector, where x3 is my scalar, x1 would be negative 1/11 of whatever x3 is, x2 would be 18/11 of whatever x3 is, and then x3 is clearly itself, right? That's terrible. Whatever, you get the idea. But that's the point, is you can think of it as, so first off, there are infinitely many solutions here, right? But what it is it's any scalar multiple of this vector, negative 1/11, 18/11, and then x1 is 3, right? Whatever this one is, multiplied by 18/11, that's what x2 is. Multiplied by negative 1/11, that's what x1 is, okay? Or the solution set to this equation, or the span of these three columns here, right, would have to be some scalar multiple of this one, right? These would be, well, no, then that is not true, because this is the solution set to it, not what you're spanning. That's totally wrong. Forget I said. Don't do that. That's something different. So the point here ultimately is you have a dependency. Okay. So since you have a dependency, you do have non-trivial solutions. Okay. But do realize the trivial solution is here, right? Because if x3 is 0, 0 times 0 times 0, still going to be 0. So x3 being 0 would generate the trivial one, right? So do keep in mind the trivial is always there. This one just happens to have only the trivial. This one has the trivial, but it's got a whole lot more scalar multiples of that vector, basically, right? Those would be solutions to that, not the vectors that we generate. Those would be the solutions. Something different than span. All right. So let's check this out and kind of ramp this up, and it kind of will all come together. You'll see. All right. So let's say I gave you this matrix A, right? And I wanted to, here's this vector B. So I want to find the solution set AX equals B. So what vector could I multiply A by that would get to B? Or I'm looking for linear combinations of these columns to get to this one. Okay. Or is this in the span of these columns? Asking the same question. Okay. But they're all saying basically how you set it up. Okay. You take your negative 2, 0, 6, 1, 1, 2, 2, 3, 3. There's my A. And I'm going to augment that with my B, 4, 2, 8. Again, you could do this by hand, whatever, but let's just row reduce it. I'm here all day. Right, so we are storing a 3 by 4 again, negative 2, 0, 6, 4, 1, 1, 2, 2, 2, 3, 3, 8. And let me check. Negative 2, 1, 2, 0, 1, 3, 6, 2, 3, 4, 2, 8. Right on. Okay. And I want to row reduce that. Okay. So when you row reduce this, but you see kind of what you can kind of, it's kind of like that first one here. You see how you have all three of your main variables, they're all pivots. So that means in this case, you're going to end up with a unique solution. Okay. So here you're going to get 1, 0, 0, negative 2, 0, 1, 0, 4, 0, 0, 1, 0. So what does that mean? You are indeed going to get a unique solution, namely negative 2, 4, 0, right? X1 is negative 2, X2 is 4, X3 is 0. right? So that is the one and only one vector that you can multiply A by that would generate B. Or negative 2 of these plus 4 of these plus none of these would generate that, right? You can kind of almost see it like negative 2, that, see, that'd be 4 plus none of those plus none of those. Oh, look, there's 4. Negative 2 plus 4 plus none of those. There's your 2. Negative 2 of these, 4 of these plus none of these will get you to 8, right? Maybe you can see that. But anyway, that's a unique solution. Okay. Now there's a larger point here, but just wait. Let's say I wanted to find the solution set of the homogeneous. Okay. And if you're kind of the point here is, if you're following where this is going, you could probably answer this question faster than it would be to write anything down, right? You should be able to just tell me just by looking at it what this is what would be good in class, right? So basically, the point here is the only way you're going to get a solution is with the trivial one itself. There's no way you're going to end up with anything other than the trivial solution. Why? Okay, go the long way. So technically, it's negative 2, 0, 6, 1, 1, 2, 2, 3, 3, right? There's my A. But instead of augmenting with B, now I want to augment it with the 0, 0, 0. Okay. Then technically, yes, you could go the long way. Okay, so you can use the calculator, sure, right? Still the same thing, but now the only difference is that last column is going to be 0, 0, 0, right? As a check, you call up A, right? So there it is, negative 2, 1, 2, 0, 1, 3, 6, 2, 3, 0, 0, 0. Okay. But if you row reduce it, the point is those first three are never going to change, right? And that's the whole idea. This, when you augmented this with this B here, it's still going to generate that. It's the only thing that's going to vary is that last column. This here, that A here is still going to generate 1, 0, 0, 0, 1, 0, 0, 0, 1. And the point is if I augment it with B, no matter what I do, right? I mean, do it by hand, right? You switch these, not going to change. Multiply this by negative 2 or 3 or 6 or whatever, not going to change, right? You do any of those row operations, that last column, since it's all zeros, is never going to change. So the key here is, since all three of these are pivots, if I augment it with 0 instead of anything else, you're still going to end up with that same ones across. And then you can just read off 0, 0, 0. Right? So basically, hopefully you can kind of see where this is going to go, these two things together. Okay? If the homogeneous system has only the trivial, then what does that mean about any vector I try to augment it with this? You're always going to get a unique solution, right? No matter what I augment it with, the first three are never going to change. You're always going to end up with the unique. So basically, you can see how these relate. If this has only the trivial, any vector that you augment this with will always have a unique. If this has only the trivial, then what does that mean about the span of these three columns? They would have to span all of R3, because again, it doesn't matter what I get here, what I augment it with, you're always going to unique solution and always get to everything in R3, right? And so you can kind of, that whole logically equivalent, right? And it goes the other way as well, right? It's like an if and only if, meaning if you started with the fact that you always have a unique solution, then that it would also imply that this also has a unique solution, which you would have only the trivial, right? Okay, let's ramp that up. Basically, this next two examples are the exact same question, right? AX equals B, corresponding homogeneous. AX equals B, corresponding homogeneous. Hopefully, you're going to see that something different is going to happen here, okay? But same thing. Let's say I started with this A here, and I want to figure out, could I multiply this matrix by a vector X to generate this one? Or can I find linear combination of these vectors to generate this one, okay? So usual stuff. You take your 5, 1, negative 13, 1, 4, 5, negative 2, 7, 20. There's my A, and I'm going to augment that with 53, 3, negative 36. And then row reduce it. All right, again, it's just calculator. So now we are talking about a 3 by 4, 5, 1, negative 13, 53, 1, 4, 5, 3, negative 2, 7, 20, negative 36. Crap, something. 5, 1, negative 13, 53. 1, 4, 5, 3. Negative, oh, there we go. Negative 2, 7, and 20. Negative 36. There we go. All right, let's check. So we got 5, 1, negative 2, 1, 4, 7, negative 13, 5, 20, 53, 3, negative 36. Okay. So now you row reduce this. But here's the point. It doesn't matter what you augment that with, right? That A, the first three columns are always going to row reduce to that. Depending on what you augment it with, that's going to change. But that the point here is A is always going to row reduce to 1, 0, -3, 0, 1, 2, 0, 0, 0, right? This particular B that we augment it with is when you know row reduce it is going to turn it into 11, -2, 0, right? So I guess kind of the point is what might help here is I know there's more to do here. We still got to answer more questions. But what if I wanted to find the solution set of the homogeneous A is equals 0? You would do the same thing, right? 5, 1, -13, 53, 1, 4, 5, 3, -2, 7, 20. Oh no, 0, 0, 0. That was the whole point. Right? Here's my A, and I want to augment it with Z with my 0. So you could throw in a calculator if you don't trust me, but basically that 1, 0, -3, the 0, 1, 2, and the 0, 0, 0, that A, right? The first three columns is not changing. So this is not going to change. The only thing that's going to change is this. But this one happened to be the 0. No matter what I do, that one's never going to change, right? It's always going to be 0, 0, right? Whatever the row operations are. Okay. All right. So now here's the point. Okay. So does this well, first off, does there exist an X that will solve this, right? Is there a vector that can multiply A by to get to B? Yes. As a matter of fact, it would be infinitely many of them, right? Because you got a free variable here. Okay. Same question. Does this have non-trivial solutions? Yes, there would be infinitely many of them. Okay. All right. So let me hold off on that. It might be you may not be able to jump to that just yet because I want to write it as a vector form. But let me write it out the long way. Make sure you see what this is saying. So remember, this is saying x1, no x2 minus 3x3 equals 11. Then this is saying x2 plus 2x3 equals -2. And then x3, since that's your non-pivot, that's your free variable, right? What might help another way to write that is think of it as x1 by itself. I can move that over. So it's like 11 plus 3x2, right? Same thing here. You can move the x3 part over. So then x2 by itself would be the constant -2 minus 2x3. And then the whole point here is x3 is free. Okay. But we can actually write this as a vector x. Okay. Now, I know this is weird looking because like x1 has two pieces to it. It has a constant and the variable part. X2 also has a constant and a free variable part. And then X3 kind of does too. It's just that there is no constant, 0, and the X3 part is itself, right? So I could actually write X as a linear combination of two vectors. I can write it as the constant -11, 2, 0, wait, plus X3, 3, -2, 1, right? It's one of those, let me write it and then you'll see once I write it all out. So what is this saying? 11 plus 3 of those x3s, -2 minus 2 of those x3s. And the last one's kind of weird, but look, there's no constant, and then x3 is basically itself. So x3 is itself, constant plus so many x3s, constant plus so many x3s, right? It's the same thing that we did here, right? With this one, it's just that it was all constant, right? This one here, the free variable, see how it's just a constant there, but there's no constant. Okay. So, well, here now we'll talk about how this relates, okay? But think about how the homogeneous one looks. Again, columns are exactly the same. The only thing that's going to vary is this, but that's not going to change. You can check it on a calculator if you don't believe me. But basically, what's going to happen is this is basically saying the same thing that just without the constant part, right? X1 would be equal to 3x3, and then x2 would equal -2 of the x3s, and then x3 is free. Or my vector x would be the scalar multiple x3 of the vector 3, -2, 1. Right? Because there's 3 of these, -2 of these, and then x3 is itself. Okay. But here's the ultimate point. if basically if the homogeneous deal has a free variable, if there's infinitely many, then that is going to be the dependency. That's going to be where the variable part is. Okay. If you're talking about any other non-one, look, the variable part is exactly the same. The only thing that's going to vary is it might have some extra constant to compensate for it starting at a constant, right? So the homogeneous solution is going to be part of the non-homogeneous solution part. So basically the punchline is if you're talking about a non-homogeneous system like this, and it does turn out to have infinitely many, then you can see the homogeneous part right here plus some other starting point, if you want to think of it, right? It's kind of like mx plus b, right? This is your the variable part, the mx, and this is the starting value. This is like your b, right? It's the same idea. This is the homogeneous part, and this is the non-homogeneous. Right? Side note to this would be a great question to ask in class. What is that telling me about the span of the columns of A? I should have done. I put that on here. It's a great question. What does that mean? What is the span of the columns of A? Well, at least you should. I didn't even talk. Um, so just get used to that notation. So if I think it was A1, A2, A3. So I'm talking about A1 here is this, A2 here is this, A3 here is this. Okay. So first off, here's the deal. If the homogeneous equation has non-trivial, that means there's infinitely many of them. Okay. That means anybody that I can actually get to that's not the zero vector, I would get there in infinitely many ways. But if there's a row of zeros, that would mean there would have to be some things I can't get to. So what does that mean? The span would have to be some subset of R3. Or you guys remember that notation? It's like less than, but it's like a U. So this is the notation for subset. Okay. Meaning, imagine if here's all of R3, there would have to be some vectors that I can get to, right? That would be the span. But then there would have to be some other vectors that I can't get to, right? Because there would have to be certain vectors that when I augment it with would produce 0, 0, 0, blah, but not zero there. So that would have no solution. So again, putting it all together. If your homogeneous has only the trivial, that means every single vector that you augment it with will always have a unique solution. The columns would span all of R whatever. In this case, 3. If the homogeneous system has non-trivial solutions, there's infinitely many of them, then you can write it as the, any augment, and no matter what I augment it with, if I can get there, there would have to be infinitely many ways to get there, which would be the variable part attached with the homogeneous plus some constant. But that also means the span would be not all of R3, because there'd be some I can't get to, right? All right, so let's try one more just to make the point here. So same thing, right? I mean, laziness. So I'm not here all day. I want to take A and augment it with B, right? I'm going to take this A, augment it with B. Same question, just different matrix, different B. Okay. So to start off with, it's still a 3x4, right? So it's 3, -3, 6, -9, -1, -2, 3, 4, -4, 8, -12. All right. Let me check. 3, -1, 4, -3, 1, -4, 6, -2, 8, and then -9, 3, -12. All right. So now, if we row reduce that, right, it's going to turn out to be this. Okay. Let me just write it down. So when you row reduce this turns out to be 1, -1, 2, -3, 0, 0, 0, 0, 0, 0, 0, 0. Mm-hmm. Okay. Well, what does this mean? Well, you definitely have a solution, right? There's no non-solution here, right? So that means I can't get to this B, right? There's got to be some way to get there, right? I definitely have a solution. Okay. But now the difference here, notice, is that there is only one pivot. Both of them are non-pivots. So that means you're going to have 2 free variables. Okay. Now, if you get good at this, you can maybe jump right to this, but let me write out what this is saying. Again, this is really saying x1 minus 2x2 plus 2x3 happens to be -3. But that's it. That's all I've got, right? All I know there is that's how x1 is related to x2 and x3. X2 and x3 are both free variables. Or what this is really saying is that x1 is 2 of those x2s minus 2 of those x3s minus 3. Okay. That doesn't matter the order that you write it in these three things. So if you want to put the constant first, whatever, it doesn't matter. Okay. But the point here is that x1, see how it's got three different components to it? It's got the x2 piece, it's got the x3 piece, and then it's got the constant piece. So what we're talking about is a linear combination of three vectors. There's the x2 piece, the x3 piece, and then the constant piece, right? So, no, what am I doing? This is the whole vector x now, right? So the whole vector x, x1 would need two of these, it needs -2 of these, and then it needs a constant of -3. This is weird, but x2 would need itself, doesn't have any x3s, and then it doesn't have a constant. X3 doesn't care about x2, it cares about itself, and it doesn't have any constants. Right? So there's your 2x2 minus 2x3 minus 3. That's how x1 is. Then x2 is basically itself, right? x2, nothing, nothing. Nothing, x3, nothing. Right? So x1, x2, x3. Okay. But the point is it's a linear combination of those three. Okay. There's more. Hold on. What if I wanted to solve the homogeneous now? Well, it's basically the same thing. You're going to take A and augment it with the zero vector. Okay. Hopefully, you could, without using the calculator, you're going to see that the first three columns, 1, -1, 2, 0, 0, 0, 0, 0, 0, those are not going to change, right? It's the same A. The only thing that's different now, this is a zero vector. But it doesn't matter what I do, this is still going to end up being 0, 0, 0, 0, right? So now, what are we talking about? We're talking about x1 minus, oh, what did I do here? This should be a -1. Crap. This should be a 1. So then this should be a 1, and then this should be a 1, right? But the point is the same, right? Because this is a -1. I just wrote 2 there for some reason, right? So it should be x1 minus 1 of these plus 2 of these equals -3. And then when you move that over, it's 1 and x2. So that should just be 1. Okay. But anyway, the point here is this is going to be x1 minus 1, x2 plus 2x3. But now it equals 0. Or x1 would be x2 when you move it over minus 2x3, but then you got 0. But again, what would the overall vector be? Now it's only two vectors, right? You got the x2 piece and you got the x3 piece, right? But to get to x1, you need one of these and -2 of these. X2 needs itself, but not has nothing to do with x3. And then x3 would need itself and none of these, right? All right, but ultimately, what is the point? The homogeneous solution here, you can see right in there, right? And it's the same basic punchline as no matter how big that free variable, how many free variables there are, it doesn't matter, right? The whatever the solution to the homogeneous deal is, if it has a free variable or multiple free variables, I could augment it with anyone I want, and the free variable part is going to be here. You're just going to have some extra constants to get to whatever vector you wanted, right? Or you could generalize it. Suppose the equation AX equals B is consistent for some given B, and let P be a solution. The solution set of AX equals B is the solution of all vectors of the form P plus V sub H, where V sub H is any solution of the homogeneous equation. Woo, that's a lot. Don't get lost. So hold on. So think of it first off. It's written this way so you can see it, but it goes both ways, really. So think of it as AX equals 0. Let's say it has a solution. Now they write it as V sub H here, so you can see it's a vector V, sure, but there's sub H, so they know it came from the homogeneous deal, right? So let's say the homogeneous has a solution, okay? If I look at any other one here, okay, it's going to be written as some constant plus whatever the solution is here, right? So like, actually the easiest one there, you know, it's tricky, but this would be like what they're talking about here is, you know, we're talking about A augmenting with B, right? We're trying to get to some other non-zero. This is the V sub H, and this is that P they're talking about, right? There's a constant plus the variable part. Same thing here. right? This would be the constant, and this would be the variable part, right? But no matter how many free variables there are or how big things get, if you're trying to look at a non-homogeneous system here, if there's infinitely many, the variable part is gonna be inherited in the homogeneous. You just got to tack on the scalar, or, the starting point, right? The extra piece, the extra vector you're starting with, right? It's weird, but it even works here. So technically, this would be your v sub h. But if you think about that, if I added the vector 0, 0, 0, it's still there, right? So even if you had a unique solution, you still have a p and you still have a v sub h, right? It's just that happens if there's only the trivial, then it's really kind of trivial because you're adding nothing, right? So the ultimate point here is, think of it as, no matter whether this is 0 or anything other than 0, if this has infinitely many, you can just look at the solutions of the homogeneous and then adjust by some constant, right? All right. So let's see if that's done. So let's check this out. Let's let A be rho equivalent to this. Okay. And I want to describe all the solutions of this AX equals 0. Now, okay. It's kind of deep. You got to take a little bit of leap here, right? So there's some matrix A out there. Where did it originally start at? I don't know. I have no idea actually what A is, right? Because it doesn't tell me what A is. It says let A be rho equivalent to this. So that means there's some matrix out there called A. They did some work, they rho reduced it, and they ended up here. They transformed it. Okay. Now, could you read off all the solutions? Well, whoa, whoa, whoa. Wait a minute. Wait, before you just jump to it, realize that this, well, I should say this technically, this, this, those are your pivots. So this is, they kind of did part of the work. They reduced it sort of, right? This would be in row echelon form, but it's not in reduced. So you would have to do some more work to get in reduced format. Okay. Mm-hmm. All right. There we go. So so 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, right? So this is the 4 by 6, 1, negative 2, 3, negative 6, 5, 0, 0, 1, 4, negative 6, 5, 1. Okay. No, I don't want B. A. So let me check. 1 zeros, negative 2 zeros, 3 zeros, negative 6, 1, 5, 4, 0, 0. And then that last one was 0, negative 6, 1, 0. All right. So there's my A. If you would indeed row reduce this, I mean, reduce row echelon form of it, not just the row echelon form of it, right? It's going to end up being 1, negative 2, 3, 0, 29. So it's going to be 1, negative 2, 3, 0, 29, 0. And then 0, 0, 0, 1, 4, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay. All right, so then what does that mean? Now, I know everybody looks at this and say, oh, look, right, you got a row of zeros with a 1. That means you got no solution. No, no, no. Hold on. Remember, this is not an augmented matrix. This is just your original A, right? So what we're talking about here, I know the context is weird here, but remember, you're talking about this matrix A. We're multiplying by some vector X to generate the 0, right? So technically, this is your A, but we're row reducing it with that 0, 0 is really your augmented part. Okay, so this is just the coefficients. So we are indeed talking about 1, 2, 3, 4 equations, but there's 1, 2, 3, 4, 5, 6 actual variable. Okay. So also keep in mind, what actually is A? We don't know. I don't care. It doesn't matter. A happens to reduce to this. You reduce it even more to this. But could you still tell me the solution to this, even without even knowing what A is? Sure. Let's see if we can just jump right to this without writing it all, right? Because keeping in mind that, well, I should do this. Pivot, pivot, pivot. Free, free, free. So basically, what this is saying is that X1, 2, 3, 4, 6. Those are your pivots, and X2, X3, X5. These are your 3 non pivots. So those 3 those are going to be your linear combination of the vectors that we're talking about. So your solution set in general is going to be some combination of x2 plus some combination of x3 plus some combination of 1, 2, 3, 4, 5. Right? So then from here, I want 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So x1 would need 2 of these. It would also need -3 of these. Right? And then it would need -29 of the x5s. Okay. Now, x2 is a free variable, so it needs itself. It doesn't care about x3, and it doesn't care about x5. x3 is a free variable, so it doesn't care about x2, it cares about x3, and it doesn't care about x5. Should have made these bigger, sorry. Then x4, now see 1, 2, 3, 4. x4 would be -4 of these x5s, right? But it doesn't care about x2 and it doesn't care about x3. x5 is a free variable, so this would be 0, 0 in itself. And then 1, 2, 3, 4, 5. There's one more. X6 itself is 0, so it doesn't care about anything, basically. So yeah, sorry, it should be this. Right? But you can hopefully see x1 needs 2 of these, 3 of these, -29. x2 is a free, x3 is a free, x4 needs -4 of these and nothing else. x5 is the free one, and then x6 itself would be 0. Right? So just being able to read off the solution there as well. Okay, but now here's the point. For some b, what is the b? I don't know. It turns out this is a solution of ax equals b. Could you describe all the solutions? So I know there's a lot of hidden stuff going on here. So remember, the sum matrix A. What is A? No idea. But I do know that it reduces this. It reduced row echelon forms to this. Okay. There's also some other vector B out there. What is B? Don't know. Don't care. Okay. But if I take A and multiply by this, you're going to get to here. But here's the thing. If the homogeneous deal here, if the homogeneous ones has infinitely many, if this has a solution, then it would also have to have infinitely many, right? Because if the homogeneous has only the trivial, then no matter what B is, you're only going to end up with the unique solution. But since the homogeneous has infinitely many, then the ones that I can get to would also have infinitely many. And the point is basically this is the variable part. This is that constant part. So your solution to this would be the constant part plus the variable part. So all the solutions of x would basically be that constant part, -1, 3, 5, 2, plus, well, that doesn't make any sense. That can't be a solution because you only have 4, right? I mean, well, let's pretend 1, 2, 3, 4, 5, 6, right? Because there's got to be 6. Otherwise, it doesn't make any sense, right? Because you got to have 6 variables 1, 2, 3, 4, 5, 6. Typo, my bad. So let's pretend those were 6s there, right? 1, 2, 3, 4, 5, 6. So it's got to be -1, 3, 5, 2, blah, blah, whatever it happened to be. But then basically the point here is then you would have the variable part. X2 would be the 2 ones, 1, 2, 3, 4. And then x3 would be this -3, 0, 1, 0, 0, 0 plus x5 is the -29, 0, 0, -4, 1, 0. Right? So that had 6s there the whole time. Otherwise, it wouldn't make sense. But hopefully the point is all that really matters here is you have a constant, and then here's your variable part. So that's the p they're talking about, and this is the v sub h they're talking, right? But yeah, this is like the mx plus b, right? All right. So logically, let's think through some of these. Let's say I don't give you an a, but can we think through these things? So let's let A be a 3x3 matrix with exactly 2 pivot columns. Does the equation x equals 0 have a non-trivial solution? What do you think? The answer is yes. Okay, it would have to have non-trivial solution. Because if there's exactly two pivots and they're 3 by 3, that means it would have to be one non-pivot, right? So that means if there is one non-pivot, if there's one non-pivot, then that would imply there has to be a free variable. If there's a free variable, you've got non-trivial solutions, right? So just kind of imagine you could like a 3 by 3. So imagine a 3 by 3. Okay. You could have something that looks like 1 0 0 1 and then 0 0. There could be some number here, some number here, right? So the first two columns could be there, or maybe it's 1 0 0. Well, zero actually. This could be like whatever 0 1, and then it's 0 0. Maybe it's the first and the third. If that were the case, then again, you still have a pivot, right? So you could see different examples of it. But if there's two pivots, there's got to be one non-pivot, which means there's a free variable. So there's got to be a non-trivial solution. All right. What if I had A and B? Does the equation AX equals B have at least one solution for every possible B? That would be no, right? So if you had, so okay, if you had two pivots here, then there would have to be 0 0. What that means is it's potentially possible to augment that with a B where you had a blah, blah, and then there could be a number here, right? So if you had two pivots, if you have a free variable, that means now this could be a 0, right? You're right. If this could be a 0, then that means you could get to that vector B infinitely many ways. But there would be other vectors that would produce no solution, right? So think of it as some of the B I could get to. The ones I get to, I can get to infinitely many ways. But that means there would have to be some B I can't get to, right? So it's possible to end up with no solution, right? Keep in mind, this is the same thing as saying the span of the columns of A, whatever they happen to be, is not all of R3 then, right? Same, that's the exact same thing. If there's some I can't get to, some with no solution, I can't get to everything.